Welcome to Solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
All right, so here it shows us a reaction in which we take a 4-carbon chain that's in the cis form and we transfer it to the 4-carbon chain in the trans form. Ask us if isomerization requires breaking of this pi bond, what minimum energy is required in joules per mole and also joules per molecule. So in order to answer that, we're going to need some data that they don't give us. Specifically, we're going to need to know about carbon-carbon bond energies. So we're going to be breaking this pi bond. Remember that each double bond is 1 sigma and 1 pi bond. So we have a carbon here. They have a sigma overlap. They also have a pi overlap. So this sigma overlap is going to remain. So it can just rotate in place, and that's not going to change the energy, whereas the pi overlap has to break. So we need to know what the energy of a double bond is. On average, it's about 602. So we can take that. But we don't need to break the single bond. So we only need to encounter the energy between these two. So we can subtract off 346 for the average single bond. So that's going to leave us with 252. And this is in kilojoules per mole. Just these units here. So to get that into joules per mole, you simply multiply by 1,000. To get it into joules per molecule, we need to divide by Avogadro's number. Remember, Avogadro's number is 6.022 times 10 to the 23rd. And this is molecules per mole. So if we divide by this, the moles are going to cancel out. It'll just leave us kilojoules per molecule. That'll be the answer to question A. And now we need to know if the energy for this isomerization comes from light, what minimum frequency of light is required. So we're going to need that number that we calculated for joules per molecule. And we're also going to need to know, so that tells us how much energy is in the light. But we don't want the answer in terms of energy. We want that in terms of frequency. So that means we need the relationship E equals h nu. All we had to do here is divide by Planck's constant, which is 6.626 times 10 to the minus 34. And that'll tell us our frequency in meters. It might be easier to look at that frequency in nanometers. And the answer you should get is that this is in the infrared, or sorry, the UV portion of light.